Hello, everyone. Welcome to the seminar on practice problems. And this is a key initiative of the MSOM journal. The goal of this initiative is to bring the voice of the practitioner closer to the OM community to inspire and facilitate exciting problems in different areas. And this is our third seminar this year and probably sixth in the series. And we have covered a variety of topics from healthcare, retail, biomanufacturing. And today we are going to talk about energy transition. Our guest co-host for this seminar is Professor Nicola Secamandi, and he's a professor of management at the business school in the Rice University at Houston. Nicola is a leading expert driving academic research in energy industry in the OM space. And I will hand it over to Nicola to introduce the speaker and also moderate the question and answer with other participating editors. I just want to point out that this seminar is recorded, and I encourage everyone to engage in the seminar by asking questions via the chat in Zoom or by raising your hand and unmuting yourself and asking the questions. Nicola, over to you.
Thank you, Pavitra, for the kind introduction. So let me introduce Yaran. So Yaran founded Rystad Energy in 2004, and he has been managing the company since then. Yaran has extensive experience in the energy space. His expertise spans the whole spectrum from fossil fuels all the way to renewables, and in particular, all aspects of the energy transition. He has a master's degree in physics, and his academic background also includes philosophy. He's a frequent keynote speaker at international energy conferences, and we're fortunate to have him here today. Floor is yours, Yaran.
Thank you. Thank you for the opportunity to talk to you, and great to meet you all. Meet you all, and feel free to ask questions. And but I will try to speak for like 45 minutes, and then have 15 minutes for Q&A also in the end. But also, if you think it's you need it, you can also try to interrupt me when I'm talking, while I'm speaking. Also, maybe I then say that I will come back to this. I don't know. So let me, so very briefly, we just Rystad Energy, for those that don't know us, we are an institution of 700 people now in 35 offices doing energy intelligence every day. So, and I'm heading up the company, but I'm also particularly engaged actually in the energy transition, and are doing quite some research on that also. So hopefully you can now see my screen, and my title today is towards a clean and lean energy future. And I think that the first word should be familiar to you. Clean, of course, a green future without greenhouse gas emissions. But I also have a point about using the word lean. And this is about the material flow associated with the new energy system. And my key point there is that we will actually see overall much less materials used and much less logistics in the future energy system. And this is maybe on the contrary to what many people fear, that we will be lack of materials, etc., for the future energy system. So hopefully I will have time to get to that part of the presentation as well. But I'll start with a very big picture to look at 300 years of energy history. So from 1800 to 2100. And what you see on this slide is the top line above the gray field is the primary energy consumption globally, increasing from about 10 exajoule in 1800 to around 600 exajoule today. So exajoule is what we usually measure the global energy consumption in. For those that are more familiar with barrels per day, it's about 300 barrels per day. 600 exajoule is approximately 1 to 2. But what you see is that, yes, energy consumption has grown, but I'm here predicting and indicating that the peak energy will decline after a peak energy consumption in the 2020s. And how can that happen? That is a big puzzle for many people to understand. But as you see, the end user segments they are getting increased access to energy, both the buildings, the transportation sector, and the industry sector, industrial sector, as you see those three sectors. But associated with, this indication that we are actually seeing a peak primary energy and a decline, this is because the energy transition means the biggest revolution in energy efficiency that we will have. Why, when we are moving from an energy system based on molecules to an energy system based on electrons, physics, from chemistry to physics. And in chemistry, we are putting the energy name of the gasoline, for example. We are saying that 1 liter of gasoline contains 36 megajoule, or 10 kilowatt hours if you want. But really, if you look at that, if you're consuming that and burning that gasoline to move your car, only about 1/3 of that energy is actually used to move the car. 2/3 of that energy is heat losses to the environment. And the same is the case if you're burning gas, oil, or coal to make electricity. Then also 60% is heat losses to the environment. And in some cases, you can use that heat for industrial heating, for example, nearby, if you have nearby industries. So you can have so-called cogeneration. And then you can have slightly higher efficiency than 50%, even 55 to 60%. But still, there's large losses. But when you are harvesting electrons directly from solar or from wind, and so that so the electrons is the current, the electricity is the prime energy carrier from the very start, then the energy efficiency is much higher. The energy losses, even in and out of batteries, it's much smaller than energy losses compared associated with fossil fuel. So this is the explanation why we will have peak energy and decline, but at the same time increasing access to energy for all the end users globally. And these end user segments, it's calibrated country by country. It's increased to and it's going to feed the energy need of a global population of 10.4 billion people in 2090, which is the UN's mean case of population. And also with increased GDP and wealth growth all over the world. So this includes wealth growth in India, Indonesia, in Bangladesh, in Pakistan, in Africa, etc. It's already accounted for. And also every megajoule you're actually using as an end user, the energy service you get out of it is larger and larger. Because, for example, buildings get better and better. The doors, the windows, everything is better insulation. So you need less energy to achieve the same comfort in the building. And also energy efficiency, for example, in LED lights versus old-fashioned light, it's up to a factor of 50 times more efficient. So we get the light you need with much less energy consumption. So we have really looked at the energy services needed to feed a population hungry for energy. But still we have this conclusion that we will see peak energy and a decline. But the condition for this is that we are going from a fossil fuel energy system to a renewable energy system. And I will show you what that looks like in terms of primary sources of energy. And you see here from the bottom, we have traditional biomass, you have coal, oil, and gas. And these 4 sources, at least the 3 fossil fuel sources, will be outcompeted here by solar, wind, hydropower, geothermal, and biomass, as you see, and some nuclear. And so these, and since these energy sources, with the exception of biomass, is directly production of electrons, we get this energy efficiency revolution that I talked about. But talking about revolutions, it's actually been quite some revolutions along those 300 years. And this is not the first energy transition that we have. And it's more easy to see this if I scale the axis up to 100%, like you see here. Then we can actually see that there's 4 different eras of energy consumption. So up to 1860, biomass, wood was dominant. But then coal came in, and coal was used in all kinds of applications: transportation, heating of buildings, and electricity production, and also in metal production and other industrial production. And coal was completely dominant for almost 90 years. But then in the 1950s and 60s, oil and gas came in and took over the market share from coal. And that was a quite sudden revolution. And now we are facing the third energy transition, with renewables taking over from the fossil fuel. But to study this systematically, we have developed in Rystad Energy what we call the energy system map, which is a quite comprehensive system to put all the different energy sources in a context and see how we can balance this energy system. And this is the map you see here. So just to briefly explain this for you, on the left-hand side, you see that 12 primary sources of energy that you are harvesting from the nature. From the top, solar, wind, hydro, geothermal, energy crops, uranium, gas, oil, coal, and then traditional biomass. And also waste, as you see here from the society. And this energy can be then brought to the end users on the right-hand side. So for example, for solar, wind, and electricity, you see these 3 lines. If you look down to the right, you see that the description of 3 lines means electricity. So electricity directly to the buildings, or via battery storage, as you also see. Or you can even use that electricity to produce hydrogen, as you also see in the second column from the top. So from electrons to molecules. You can also use heat directly from geothermal, directly through district heating to the houses, or even through a steam turbine to produce electricity. Or you can use the molecules as molecules, but you need to upgrade them to standardized molecules, which is the second column, with refineries, gas processing plants, and biogas plants, etc. And in the mid column, it's all the power plants globally. So nuclear power plants, bio boilers, but also gas, fuel oil, and coal power plants. And from those is both heat and electrons going to the end users. And the fourth column is all the energy storage and distribution, as you see. The grid, from the top, the battery storage, hydrogen storage, pumped hydro, district heating, biomass logistics, the grid, and then the transportation of fossil fuel. So this is the overview, as you understand. And those end user segments, you see 30 different segments on the right-hand side. The reason why I'm including exactly these segments is that we have a very good historical reporting on the consumption for each of these segments by country. It's called the Eurostat data. So you can, if you dig deep, you can access data country by country for this segment by segment, with about 60 different energy carriers that are also introduced on this page. So this is the framework, and we can use this to study historically what has happened. And the energy system I started with was based on wind for shipping, and coal for some heating and metal production, and then the rest was wood. But this energy system came into a crisis in the mid-18th century because all the forest in Europe, for example, was gone. This is the forest coverage in Europe before the time of the Roman Empire, 3,000 years ago. And this is the forest coverage in 1850, meaning that most over Europe, these red zones, is less than 10% forest left. So all the trees were cut down, and it was an energy crisis in Europe. And only since we got coal, the countries were able to continue the industrial revolution. So this was what it looked like most over Europe at that time. And also in parts of America and other places globally, we kind of exhausted the resources, the current biomass resources. You could say the same about whale hunting, for example, in whether it's outside Nantucket or Martha's Vineyard, or other places with a lot of whale hunting. Took all the whale oil, and then it was almost extinct at that time. So then coal was a relief, and we got a coal society with hot water heating, with warming, with as you see here, with stoves that also heated houses, but also for transportation and for steam engines, etc. That was a big revolution. That was the key energy source until 1950. But what happened then? Yes, we got some disruptive technologies coming in. And one in the transportation sector, this was this diesel electric train, as you see here. And from coal consumption in the transportation sector peaking at more than 200 million tons in the 1920s, then a cyclical downturn, a cyclical upturn during the World War, but then a structural downturn after 1945. In 1945, actually, people in America saw a big growth after the World War II, expected economic growth. And it was a fear that it was not enough coal to feed the transportation sector. Because coal was the only source of that was used in the transportation sector for rail and shipping for the big machines. And even if there was 300 diesel electric locomotives already in the beginning of the 1940s, people saw that that was niche applications. But it really took over because it was cheaper and better. And during 15 years, it wiped out all the existing steam locomotives in the United States. And it was a huge infrastructure that was completely eliminated within 15 years. So this just shows how fast an energy transition can go when you have a new disruptive technology. Then what came was the oil and gas era, serving us very well for 80 years. But as I already mentioned for you, the losses is quite significant. So the logic in this system is that it's better to bring the molecules all the way to the end user if you want to use them for heating or for work. The only purpose of having electricity is for applications like light or internet or things like that. So that puts an upper limit of how much electricity you can have in the system, because you would rather use the fuel directly. As I said, it's much more efficient. But with the renewable energy system that you see here, the losses are much smaller, and this is a complete net zero energy system, and I'm sure we will get there. But the question is how fast, and this is what we are really spending a lot of time trying to analyze. How fast? But then we will get to another logic of the energy system where it suddenly is logical to electrify all the end user applications. So it is a electricity revolution that we are facing now. For the first time with renewable electrons, it makes sense to heat the house with electricity and to fuel the car with electricity rather than fuel. And the scenario I already showed you is what we call the 1.6 degree scenario. As you see here, you can see that in the heading about the graphics here. So here is a slightly shorter time frame, only 135 years from 1965 to 2100. And again, you see how solar, wind, and hydro and biomass will outcompete gas, oil, and coal. And also, it's very deliberate using the word outcompete, because this is the logic that you have to implement the renewable technologies, and then the market forces will then stop asking for oil, gas, and coal, and the market forces will then shut down these energy resources, because the operational cost of coal, oil, and gas is always higher than the operational cost of renewables. So when the investment is done, you will then see those sources being phased out. So this is the logic, not to try to stop oil, gas, and coal. If you try to stop it before you have been building the competing infrastructure, you will only create disruptions, and that will just be a pain for the society. So it's important to kind of understand the logic, the sequence here. And as I said, if you're looking at the energy carriers, yes, today 20% is what is logical to have as electricity, but in the future, 60-70% in the 2050s and 60s is logical. But 1/3 of that need to come from storage. So storage technologies will be very important, and I will also look at that. But also, you see, hydrogen will grow, and actually here 5-fold. Hydrogen or hydrogen ammonia, derivatives like ammonia. This is because you need some molecules to for example, as a reduction agents in the industries, in the chemical industries, for example, or mining, to remove oxygen and other kind of molecules from when you are extracting minerals, for example. And as we have seen, you already have seen this before, the peak in primary energy, but the growth of secondary or end user access to energy. And also be aware that energy consumption, 70% of the end use is heat. But work, which is 20%, is still, you need the input of that is 3 times higher than what you're actually using. So a large share of the gray part is losses related to creating work or services, which is the top part. So this was the education on one scenario and the future, but this is only one scenario. Which scenarios do we think is most likely? Well, let's look at how we are constructing scenarios. And then we are starting actually with the IPCC report, looking at what, and this is excellent research, I think, an excellent summary of research that is done by IPCC. And you will find on the page 753 in their working group 1 report, the budgets for remaining allowance of carbon dioxide emissions. So for 1.4 degrees, 350, and for 2.4 is 2050. The difference is 1700, meaning that for every decimal degree, it's 170 gigaton. So we just add that to each, and then we get the budgets. However, they are slightly conservative, so they are rounding it down to the nearest 50. So 690 for 1.6 is rounded down to 650, as you see. But that matters, and it's a big difference between every decimal degree. 1.6 is very different from 1.7, which is very different from 1.8, both on the implication side for ecological and weather systems in the world, but also in terms of how fast new technologies need to be implemented. And what they're doing then is that they're matching these budgets with a complete energy system mix. So, of course, much more renewables if you want to go faster down. So this is just illustrations of 1.4, 650, 1.6, or 2.1 degree, then you can allow for 1,500 gigaton of additional emissions. So I think you understand now how we are constructing these scenarios, and for each of these lines, in this case, only the carbon dioxide line is an associated line for solar production, wind production, oil production, gas production, coal production, etc., which is a complete system, and that will allow for sufficient energy to feed to all the end user segments.
Yaran, Hanat has a question here regarding the role of government interventions vis-a-vis the scenarios.
Yes, I can take that immediately, because to jump to one conclusion here, I think that the likely scenarios, what we will be able to achieve, is not 1.4 or 1.5 like you see here, but it is 1.6, 1.7, 1.8, or 1.9. And I think that technologies alone will be able to drive down the scenarios to 1.9, maybe 1.8. But to get all the way down to 1.6, you need more governmental intervention, like you asked for. Then you need more carbon taxes and other incentives and drivers to bring down the last part that is not yet economical to drive down. But a lot of this energy transition will happen because the new technologies already are more competitive. And I will show you some examples of that soon. Just also be aware, yeah?
So if I understand correctly, the scenarios are independent of government interventions, but
yes,
which scenario will happen will depend on government interventions.
Yeah, as I said, the scenarios are kind of complete systems of an energy mix that will deliver these emissions. And then we can talk about what, if you are starting then, and that is where I'm going now, what is actually happening? How fast is this going? Which of these scenarios are we tracking towards? and what is the impact of governmental intervention to get to any of these scenarios.
Thank you.
So you can see this as a Cartesian kind of coordinate system of potential outcome. And then you can discuss the likelihood based on observations in the real world for each of these scenarios. That's the purpose of this. And also just to mention that, as you see, all of these scenarios are going below zero in carbon dioxide, meaning that all of them are including different levels of carbon capture and storage. I'm also coming back to that. But the key to achieve this reduction of from 38 gigaton, as you see here, down to zero, is to do mitigation of the technologies that currently are producing these emissions. And then it's good to be systematic to look at each of these technologies. And again, if you go back to IPCC, they have a very rigorous categories for how to group the different emissions. And you see that quite complex here, of course. To see those up in the right corner here, you see all the different categories, starting with 1A, fossil public electricity and heat production. And that's the biggest category. 1A2 is fossil fuel-based manufacturing in industries and construction. And then the third largest is the road transportation, and the fourth largest is residential heating. So what I'm doing now, and the methodology we have, is that we are looking at all of these emissions, and we're grouping them by sector, as you see here. And we're looking at in each of these sectors, from the most important is electricity and heat sector, then is industrial, the transportation and the buildings. Which technologies will be able replace the current technologies and to bring it down to net zero. And here you see these technologies. So for electricity, yes, solar is the most important, followed by wind. And then the next is batteries. But batteries means solar and wind plus batteries. First is solar alone, wind alone, and then solar and wind and other renewables, plus including batteries. So batteries is very important. And then it's like geothermal, it's geothermal storage, it's high temperature heat storage, it's hydrogen combustion, ammonia combustion, etc. There's other technologies. So this is very detailed study to see all of this. And then we can regroup these technologies into kind of categories of technologies. So then we have the power and heat technologies, the storage technologies, the electrification of end user segments, technologies, etc. Then we can look at the condition. Where are we in terms of speed of implementation of each of these? Then we can be quite scientific in a way to see where we are tracking. Is it towards 1.5 or 2.0 or 2.5? So this is not up in the blue, like no decision on. We can actually track it very systematically, and that's what I'm going to show you soon. But first, just reflecting a little bit on what you see now. This, to bring these emissions, you know, for example, for power and heat technologies, is responsible to mitigate 17 gigaton of emissions from currently fossil fuel to renewables. And solar, on the total mitigation, solar is 25% of all you need to achieve. And the difference is 1.5 between 2.5 degree and 1.5 degree global warming. Is successful implementation of solar will account for 0.25 degree of that. And then it's three technologies: batteries, electric vehicles, and chemical absorption, CCUS. That is this 0.12 each degree, 12% of that difference. Those three. And there's another three, which is wind, geothermal, and hydrogen, which is the next with about 0.08. And then remaining is biofuel and recycling technologies is about 0.15. So in that sense, we are able to articulate which technologies do you need successfully to implement to get to net zero. And the sooner you get to it, the lower global warming you get. And it's only technologies that will get you there. We don't see any behavioral change from people. You know, you cannot convince people to not drive a car or not to fly, but you have to change the technologies in driving and in aviation to be zero emission. So this is possible, but policies will help to stimulate people to use these new technologies faster if they get the right incentives to do it, like cheaper technologies, or that you achieve some benefits, other benefits from using them. And then, so this is the case, and then we can start to look at each of these technologies and where they are tracking, and I will show you a few of them here. So solar is what is having the best track as we speak. Solar and EVs, actually, they're tracking above expectations, faster than we expected a year and 2 years ago. Wind is tracking slower due to some cost issues at the moment. And the other technologies are tracking approximately as expected. But you see one reason why solar is very competitive. And this is the new solar farm in Abu Dhabi, 2 gigawatt. And the levelized cost here is $13 per megawatt hour. And just if you charge your electric vehicle directly from here, you only spend 0.1 megawatt hours to drive 500 kilometers, or the same as 100 kilowatt hours. And those of you that have an electric car will know that that is right. You're using approximately 20 kilowatt hours per 100 kilometers, or then 100 per 500 kilometers. So then the marginal cost of driving 500 kilometers is only $1.3. And this shows that in its best realizations like this, the new technologies combining solar and EVs are an order of magnitude more efficient than fossil fuel. At best, you would need 30 liters to drive 500 kilometers. And that is, you know, with a liter is 10 kilowatt hours. That is 300 kilowatt hours, 3 times as much energy as you need for an electric vehicle. And the cost would be, even without taxes, just below $1 per liter, or then $25 to $30. So one order of magnitude more than this. So this just shows that the energy transition is not only about getting a cleaner world, but actually to get a more efficient world with cheaper energy overall. And that is probably the driver that market forces since 2016 has been building more capacity for low carbon every year than fossil fuel. And this year we are likely to build 520 gigawatt of low carbon power plants and only 185 of fossil fuel power plants. So the energy transition has already happened in the electricity sector, and it's only, you know, a question of time when this lasts for another 10 years that it will be a complete transition in the electricity energy system. But just you thought that this 2 gigawatt was a big electricity plant. Look at this. This is in the Western Green Energy Hub in Australia. The plan is to build one single site of 50 gigawatt. And this is in areas where you have a desert area near the ocean. Then you get strong solar radiation for the whole day, and you get strong evening breezes due to the heating of the air above the land. You get the evening breezes every day, and then you get so combining wind and solar can give you a very steady supply of very cheap energy. And this is an illustration of the future super hubs of renewable energy, where you can make the cheapest production of metals and hydrogen and chemicals, etc., globally. And there's a lot of these kind of super hubs under development as we speak, in Australia, in Djibouti, Namibia, Mauritania, Morocco, Mexico, Chile, and many other places, where you have these conditions of combining solar radiation with evening breezes. Another issue, of course, is also, do we have space for the solar panels near cities? Yes, in a desert is okay, but that is far from a city. And my answer is yes, there's enormous room for innovation, just looking at applying solar panels, ideally where you have a dual function. You can use it for shade, protection for heavy rain, combined with production of solar, or here, as in California, reducing evaporation from the channels, etc. But how fast is solar going? And here I'm again back to the same from the colors. These are the scenarios for global warming that I showed you on carbon dioxide. But here I've applied the same, but for annual installation of new solar. And last, as you see, in 2015, it was 50 gigawatt, growing to 100 gigawatt in 2020, growing to 210 gigawatt last year. And so far this year, we seems to be landing at around 250 gigawatt to be installed this year. And as you see, we are tracking them slightly faster than what is required from the 1.6 degree scenario that I showed you. And then the question is, can we scale up sufficiently to deliver 1,000 gigawatt by 2030? Five-folding or four-folding the current capacity. And looking then at plants actually being built, we see that, yes, this is happening. It's scaling tremendously fast. There's hundreds of new polysilicon, wafer, and cell manufacturing factories under development as we speak. And for example, that this light green color, which is polysilicon manufacturing capacity, you will see that was the bottleneck in 2021, only allowing 200 gigawatt of construction. But with the visibility we have of factories now, it's going to sixfold to 1,200 gigawatt within only 4 years. So it is an explosion in solar capacity. And that's why we think solar will be able to deliver on this very aggressive growth line, not only to replace coal and gas in current electricity system, but also to electrify all the end user applications. However, the big geopolitical challenge with this is that it's completely dominated by China. And here we need the Inflation Reduction Act or other political incentives to avoid this geopolitical kind of vulnerability that we are so dependent on China. And let me now round off with my points on clean, from clean to lean. So yes, this energy system will clearly be clean, but will it also be lean, like you see I'm indicating here? And just a few observations. This is a building very near my house, actually, in Norway, as far north as Norway. And they have installed 10 tons of solar panels. And they have a lifetime of about 25 years, as you see on this picture. And this is replacing about 8,000 tons of coal, if that was the alternative way to feed it. So logistically, instead of moving 8,000 tons of coal around the globe to a site and burn it, you can move only 10 tons of solar panels. This is an engine from 1927, 6,000 kilos, 35 horsepower. This is a new Mercedes 2023, 208 kilos, 300 horsepower. So you see, it's been a tremendous development. Looking to the new machines from Tesla, for example, you have only 25 or 20% of the weight of the best ICE machines. So all the end user applications that will be electrified will be much leaner and smaller in the factories. And since all drivetrains, all force use in industrial sector and in the transportation sector eventually will be electrified, it will be much less materials needed, even if you need more materials for the batteries. And with car sharing, that is a consequence of self-driving cars that eventually will come. Also, families will share cars. You will just be a member of a fleet of car that will pick you up within 5 minutes, always when you need transportation services. So these are some revolutions. So looking at the total weight of fuel today, the fuel weight globally is today 18,000 million tons, or 18 billion tons. This will go down. But if you look at what that is in terms of ton mileage, it's almost 23 ton mileage that is bringing oil, gas, and coal around the world. And if you then look at total shipping globally, for example, fossil fuel is 45% of all ton mileage. And with this revolution that I'm talking about, you will take away 45% of all ton mileage related to coal, crude, LNG, and petroleum products. Even if container transport is going to grow, or agricultural products is going to grow. So you'll get peak shipping. So these are just a few illustrations why I think that this future energy system will not only be clean, but also lean. And let me round off them. So thank you so much. I'm happy to get some questions and comments.
Thank you, Ran. That was very interesting, extremely contextual information for the group. So we have a few questions. The couple related to managing these large solar farms. There's a question from Aranth about that. For example, there might be issues with cleaning the panels, directing the solar radiation appropriately, and there's a related question on the integration of these large solar farms with the distribution system, the transmission system.
Yes, good questions. Yeah, you're right that in some areas of the world, and especially in some seasons, you have, for example, sandstorms. In the Middle East, if you've been there, your car will be gray often when you are arriving in the end of the day. So that is increasing significantly the cost of operational cost, actually, of some solar panels. So the ideal areas for solar panels are actually where you don't have loose, where you have consolidated soil, and not where you have loose soil. So that increases, but you have thousands of places globally that have not have this dust in the air. But when you have it, you have increased operational cost, but still it's competitive, actually. So, but the nirvana for solar panels is the highland. What you need is cold weather and not dust, and of course a lot of sun. And nirvana is mountain deserts, like in Chile. Then there are almost 3,000 sun hours, and you have the Santiago and the markets quite nearby, and you have no dust and cool weather. So then you can have tremendously high. But most places you will have lower capacity factors. But that is not a big problem. But I think overall cost of generation in the future will be much lower than cost of distribution. The grid, it's very expensive to upgrade. So instead of making a complete liquidity of all the solar and just enough generation and enough consumption and to balance that, it will be overbuilding of local capacity, and with some local storage, and even with local kind of curtailments, because that is cheaper than having a full liquidity and to build out the grid sufficiently. But still, studies of the grid show that it's actually hugely underutilized today. So it's designed for peak hours. And with battery plants integrated in the grid, you can rather transmit a lot of power during the night or before a weather cycle or something to load one part of the country versus the other part. So batteries will play a storage. But also just digitalization of the grid, looking at the temperature, because the capacity to transmit power is very proportional with the temperature, and in cooler weather you can actually transport much more. And typically it's cooler weather when it's more wind. So when you have a lot of wind, you can actually transport much more power. So there's a lot of these examples of more higher utilization also on the current grid with digitalization. But also a lot of these big solar plants, they will be off-grid with applications in the industries like metal industry or chemical industry, and don't need to be linked to the grid.
Okay. Yeah, related questions are about batteries and more generally storage, energy storage. If we talk about batteries, will there be enough metals for building those? And a related question is, how would they be used to alleviate issues of instability, grid instability, due to the variability of the output of wind and solar? And
yes.
Then with the other questions, in particular the scenarios.
Yes, also very good good questions. And let me then take the opportunity to actually illustrate some of this, because I have it here. So you're right that batteries will be used for two, basically for do you see my screen? Oh.
Not yet.
Here. Okay, but batteries will be used for basically two applications. One is to be used in transportation systems, like you see on the left-hand side here, or batteries will be used in the grid, both upstream, midstream, and downstream in the grid. And in the 1.6 or 1.8 degree scenario, you will need up to 9 terawatt hours for transportation and 8 terawatt hours for battery energy storage. And to put it short, this means that we have to develop from currently 177 plants, and 44 new are under development, and we need to build another 400 by 2040. And we need, and lithium is the most important raw material that will be used in the battery cells. And the lithium production need to be tenfolded by 2040, like you see here. So because you're using lithium both in the cathode and the electrolyte for lithium ferrophosphate, LFP batteries. But the short answer is that studying all the mines globally, it's a lot of lithium available. Even Australia has gone from 0 market share to 40% market share in just the last 5 years. And lithium prices had a fly up, almost tenfolded from 40 to 50 to 500,000 per ton. But now it's halved again because a lot of new capacity has already come in. So basically, commodities, markets, the capitalism is working. There's abundance actually of supply of lithium. And you find it in hard rock, or you find it in the water, in the groundwater. Like you're producing it from Bolivia, Argentina, Chile, etc. You're actually doing in situ, leaching, meaning that you're taking off water wells. And even for oil and gas wells, they are starting to produce lithium now. But the short story, it's more than enough lithium globally to tenfold if you look at the details of this. And battery cost is likely to come down a lot going forward. And looking at the current learning curve, just prolong that with the capacities I just showed you, actually indicating that with the same learning curve, batteries can come down to $5 per kilowatt hours. We don't actually need it to come that far down, even if that is the vision of Tesla. We don't need it to be that cheap. Still, it will be very competitive to bring into the grid and to allow for some of this intermittency.
Good, thank you. So I think that also addresses Vincent's question about predictions in terms of availability of critical minerals. There were some other questions related to the likelihood of these scenarios. I think we touched on that already, but it'd be good to revisit the issue. So it seems to me that the scenarios are just outcomes, possible outcomes. You're not attaching any likelihood to those scenarios, but if one wanted to think about likelihoods, do you have any thoughts about that?
Yes, I think because to each of these scenarios is connected speed of wind, speed of solar, speed of EVs, etc. And we can track that. And currently, we are actually tracking at the 1.6 for solar and for batteries and for EV. And we're tracking slightly slower currently for wind. So still, but then you have to look at EV penetration, for example, need to be really see a trend shift downwards to track towards 2.0, for example. So currently we have a very quick ramp up of EVs. It's likely to be 19% globally in new sales today. So to allocate probabilities, it's actually possible to do. I haven't done it properly here, but as I said, my view is that it's between 1.6 and 1.9. That is the likely outcome. And if you ask me, more towards the lower end of this than the higher end. However, if we get a complete crash with China and stop trading with China, then they are much more towards the higher end of this.
Yeah, certainly, it's a dynamic problem to solve. Good. And then there are questions about technologies versus consumption. So there's a question about whether it's really just about technology or consumption, changing consumption will also play a role. For example, how a Tesla will be used compared to internal combustion vehicles.
Yes, as indicated with, for example, autonomous driving, that will completely change the consumption. It will actually probably be even more bespoke driving, you know, because I mean, in America, you're used to only have, you know, you're not really using public transportation, except from in New York. But in Europe and many other places, they're using public transportation a lot, but with very convenient autonomous driving, maybe even private consumption. Private will be more usual, and then increasing some of the consumption. But the material consumption will go down a lot because you will have a much higher utilization rate of the assets that you have. You know, today a car is typically only used 5% per year of the hours, or even less. So you have a very big capital lack of capital productivity. So capital productivity will be much higher, but but some consumption might be higher. And we are just not being more creative in our scenarios, that we assume that poor countries are following approximately the same path as rich countries have been following in terms of consumption going forward, but also taking into account the temperature regime that they are in, so that if you are heating degree days, how much need you have to heat your house, for example, is also taken into consideration in the scenarios.
Good, thank you. And then let's shift into recycling. Battery waste, for example. Could you give us some thoughts about?
Yes, as you so much see that one of the smaller, the last kind of 0.15 degrees of avoided global warming is very much connected to recycling and the circular economy. And today it's for some metals it's quite high, but it can be much higher. So we are assuming increased recycling of metals, minerals, and plastic, but not very aggressive assumptions. You know, plastics only 5% is recycled today, and I think we are increasing it to 15 or something. But so we have explicit scenarios showing that, and especially also in the consumption of biomass. I think that the reason for the big growth in biomass is not really because it's a very competitive fuel as such. It's much better actually to use a field for solar panels than to use it for growing energy crops, actually. But as a part of the circular economy in agriculture, to use the waste and reuse the waste, that has a big potential, and also to reuse waste and to avoid methane emissions from landfills, for example, but rather do combustion of the waste and produce power, and even with carbon capture. is a part of the solution.
Good, thank you. And there's one more question regarding investments. I suppose the question is about the amount of money that will be needed to carry out the transition, the clean energy transition for the different technologies. Or
Yes.
it could also be capacity. I think we talked about capacity. The question might be about money. How much money will be needed?
Yeah. And let me then again show you a slide, because I have just exactly that. What we are trying to illustrate here is, historically, you see, these are all investments in, this is power infrastructure. Yeah, and we also have for upstream infrastructure is slightly different, but let's start here. So the black line is power infrastructure investments, and as you've seen, that has been $1.5 trillion. I say it's not, it's wrong. It's not US billions. It should be trillions. Excuse me for that. It's 1,000 billion on the axis and 2,000 billion. So it's 1,500 billion or 1.5 trillion, which is 1.5% of the global economy. Is the historical use investments. And then on the different scenarios, you see that for the 1.4 degree scenario, you have to ramp that up to 6 trillion. And also, and 1.5, 4 trillion. And that's why I think those two scenarios are unrealistic, not only because it's difficult to get all that money, but also because the supply chain will not be able to deliver on such a abrupt ramp up. But the 1.6 is then going up to 2.2. And since this is power, and power will take over for a lot of the other energy sources, actually, I also have a curve for all, let me see, I have all of these, you know, these different investments. Yeah, here is for all energy upstream and downstream investments. And then we are at $2.5 trillion historically. And we need to have a peak of 3 trillion in the 1.6 degree scenario, as you see here. Which will then primarily investments in solar and wind and batteries. Of course, all this is based on models for current cost and with some learning curve.
Right.
So it's slightly higher than historical investments is needed, but not tremendously much. And if you look at this in combination with operational cost, and that is what I think that's what I had here. Actually, operational cost is going down much faster. With the new energy system, you have much less operational costs. So then you actually will see less total spend in to combine all the operational costs plus the upstream investments.
Good, thank you. That's a very detailed answer. I think we're reaching the end of the time allotted. Suppose there's a question though about what can be done to mitigate issues with solar panel efficiencies? Maybe if you have a quick answer, maybe we can follow up offline.
Yes, I mean, the efficiency for solar panels is a trade-off between the cost and efficiency. So I think current solar panels, typically 600 watt, is the best one. I think it's a reasonable level. It's not a big issue. So maybe I didn't really understand the question. Of course, you can have much higher efficiency in terms of how much of the radiation they are capturing, but if that is much more costly, it doesn't make sense. I mean, the space is not a big issue. So,
yeah.
so
it's partly my fault. I didn't completely articulate the question. Question had to do with locations farther away from the equator. And so what can be done?
Yes. So of course, in locations like Norway or Finland, the solar panels are much less efficient. That's clear, and you should maybe look for wind or other sources. But still, actually, and surprisingly, even as far north as Norway, Oslo, which is 60 degrees north, it is actually zero emission buildings that I just showed you this picture. We're comparing with the train, etc. So, and the coolness of the weather is a positive for solar panels, because they have much higher productivity when it's cold weather than when it's warm weather. So still they can play a role even if they have lower efficiency. But of course you need backup capacities in the cold season, etc.
Good. Thank you. So I think we have reached the end of the seminar. Thank you, Göran, for this extremely informative contextual presentation. I'm sure the O1 community will highly benefit from it going forward in doing research in this space.
Thank you so much. Thank you for having me. Great pleasure.
Thanks again.
Thank you very much.